Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the fourth lecture titled Marine Renewable Energy Systems, Analysis, Design and Development. In this lecture 4, we will talk about the wave energy converter, let us say the Indian scenario and the design parameters and associated maybe the concerns or parameters. We will talk about this. So, in the last lecture we learnt that wave, wind and solar have equal potential of harvesting, but wave energy harvest is on the side track because of various difficulties and concerns what the researchers have identified in the recent past. Now, let us apply this particular idea and see in India where do we stand, okay, what are the concerns and what are the design perspectives and what should we do to take wave energy harvesting to a forward direction. So, let us see what are the advantages India has compared to wave energy harvest. The advantages could be: one, India has one of the longest coastline. Okay, it's about 7,500 kilometers, because India being a peninsular country, we have coastlines surrounding all the three sides of the country. And to be very specific, Gujarat has the longest coastline within India. Okay, so what does it mean is, we have got a very good reason for promoting wave energy harvest. So there is a deep necessity for doing this. Secondly, based upon the research studies and literature reviewed, I can confidently say we have got a potential of wave power ranging from 5 to 25 kilowatt per meter. How to get rid of okay, yes, I got it, thank you. 5 to 25 kilowatt per meter of a steady input. Throughout the year. Of course, during the monsoons, this can even go high. This can be even higher. So, we have got a good potential. Therefore, friends, these two perspectives put us in the dire necessity of investing the ideas and research fronts on the wave energy conversion. Now, then the question comes, what would be the fundamental design parameter for which I should design the WEC converter? One of the fundamental design parameter for any system design in maritime engineering is what we call as a return period, or the design return period for which I must consider. In this case, the return period will not be associated to the device, but I would say this will be associated to the input wave to be considered. So, friends, the wave energy converters what we intend to design need not be a longer period, that is, it need not be a 100-year wave. There is no necessity. We can even have small scale wave devices. So, this will work because they are best suitable for lower energy potentials. These are best suited for lower energy potentials, and that is applicable to India very much. So, now if you look for this kind of design change, then what would be the factors or the benefits? Let us say, if you look for this kind of change in the design perspective, the benefit could be a simple design, easy and convenient installation, because the design is simple, and we can also look for a better power rating. So, now are we actually looking for grid supply connection of electricity from wave energy converter? So, what is the output target? Because we are looking for small energy sector wave energy devices, therefore, the output target cannot be a power grid connection. Okay. When you look for small scale wave energy converters, it cannot be. Then what else it could be? It could be used for powering devices used in meteorology data or meteorology measurements, can be used for reef generation, can be also used for powering desalination plants, which are all not a large kind of demand as we see in the power grid connection, but they can be very useful for short term remuneration. Okay. This was discussed and very well demonstrated by Green et al. In 1983. Therefore, our focus is now small scale wave energy converter. The small scale wave energy converters can be also placed in arrays. And when they are placed in arrays, they can also meet the power requirements of offshore platforms, not for drilling, but for day to day maintenance, electricity, generator, etc. So, this was seen as a positive note and presented by Pastor and Liu in 2014. Even my own research, Chandrasekaran et al. 2014 and Chandrasekhar and Raghavi 2015 independently verifies that there is a very good feasibility of getting larger power and substituting them for offshore basic power requirements when a small scale wave energy converter can be placed in arrays. So, now the focus, friends, is not looking for a larger harvest system, but looking for elemental small scale series of arrayed systems which can be used for this. So, independent studies conducted by me as well subsequently also confirms, like Chandrasekhar and Sricharan, papers published in 2019, 2020 and Indian patent grant confirms that about 20% of electrical needs, the basic needs, not the power generation, not the oil and gas exploration and processing, the basic needs of offshore platforms can be addressed by small scale wave energy converters, and when they are placed in arrays, they can be very useful and very compact designs. Okay. Now, further, if you look at the let us say footprint of successful wave energy converter in India, we can give only very few examples, which we can say that oscillating water column installed by NIOT maybe is the first wave powered desalination plant. and this is running successful. Similarly, the oscillating water column and other small scale devices tested for desalination plants can be a good example of footprints left in the Indian scenario for wave energy conversions. Okay. Therefore, friends, the basic drawback of going for a larger system in terms of larger wave energy converter is dealing with multi-body dynamics, which essentially means we are looking for an hydraulic PTO which need to be tuned for different damping ratios. Okay. There the question comes. This was really and clearly expressed Sricharan and Chandrasekhar in 2021. Furthermore, friends, when we look at the specific application of small scale wave energy converters, we can look for the coastal areas, islands, where grid connectivity is very bad. That is, power grid connectivity is not good. Here, wave energy harvest will be a real good boon. One can try with this. Okay. Therefore, small scale, medium size wave energy converters tailored for Indian waters. I should say small scale, medium size wave energy converters tuned for Indian waters is the need of the hour. Okay. Then let us see what are the desired features of this kind of design. The desired features which one expect from this kind of design are multi-body wave energy converter invoking participation of multiple frequencies. We already discussed about this complexity in the previous lecture also. The design what you propose should more or less remain insensitive to wave direction. We would prefer to go for floating type wave energy converter, and we should also look for adaptability of WEC to integrate with existing structures. It can be coastal structure, it can be offshore structure, and so on. Furthermore, the design should have higher scalability and it should be manufacturer friendly. So, we look for these kind of points which are to be addressed when we talk about design of wave energy converter for Indian scenario. So, therefore, we are now looking for a novel, indigenously built multi-body floating wave energy converter. That is what I am looking for. Okay. So, what parameters should we address when we start designing or thinking even about this kind of systems? So, we can now say what are the design parameters. Focus to this particular accepted agreement. Okay. So, the design parameters are as follows. One, it could be the dimensions of the float, that is I can say the size of the float. It could be its geometric configuration, and appropriate power takeoff mechanism. So, one can say they stand as important design parameters to look at this, and of course, the fourth and fifth are imperatively important. We could say that the fourth one is the design should be scalable and it should be easily manufactured. Okay. So, now look at the how do you approach this kind of design performance. That is how do we approach. Let us look at the design approach which we are now focusing at. Let us say we need to understand the necessity before we started understanding the design of this small scale VEX. The dynamic aspects, of the fluid structure interaction. We need to understand the wave characteristics. We need to understand the wave hydrodynamics, then the mechanical design aspects, and of course, experimental modeling and scaled studies, then numerical modeling and interpretation of results, and the lastly, which is very difficult to do, is the field testing, that is the real time deployment and testing it. So, we need to follow a standard methodology which should cover all these aspects. Let us say what is this methodology about? I can explain this methodology in a simple flow chart, starting from, let us say we look for wave energy converter interaction. We first try to learn this, and during learning this we have three important parameters which we need to understand. One is the hydrostatic stability, Second is the natural frequencies of the system. And hydrodynamic parameters of the input wave, which will govern the design of WEC. So, based on these, we arrive at the preliminary model, which will be actually a CAD model. We arrive at this model, okay. We will arrive at this model and get a CAD model. For this CAD model, we need to do numeric analysis, essentially in frequency domain or in time domain. We also need to fabricate a scaled model and conduct experiments. Then we need to collect the data, which is the response history of the WEC from both and compare them, right. Now, in this whole scenario, when we started discussing about the wave structure interaction, then I must also consider the possible site of deployment. Possible deployment site, then site specific wave parameters, then the energy capture principle, how I am going to capture the energy. I am going to use multi-body, single body, etc. All this itself will lead to the input for wave structure interaction. Then we go with this and develop the whole system. So, I can now say this is the overview. I can say this is the overview of WEC modeling and analysis. Okay, this is the overview. Now, I understood this, we can say this can be involved in 3 distinct stages. I can separate this understanding into 3 distinct stages. Let us say what are the stages. 1, choosing a WEC design. The WEC design can be a single point observer, it can be point observer in multiple array, it can be type of any other harness design which can harness any degree of freedom, at least 2 to have the maximum. But the WEC design should be compatible to the wave characteristics at the location of interest. So, the primary interest is the place. The second stage could be a detailed CAD modeling and analysis. Includes numerical and experimental. Of course, experimental will be on the scaled model, numerical can be on the full scale model, and one can validate and verify and compare them and see. The third could be, of course, this also has one complexity which we must recognize, that an appropriate PTO or you can try with many power takeoff systems. Okay. So, while doing so, you have concerns about the fabrication of the scaled model and also numerical analysis and so on. And lastly, we will deal with the development of technology which is technology ready. So, when you complete this, generally this is accepted as readiness level 1 to 4. Okay. The hydrodynamic wave energy converters and the ocean wave structure interaction are actually complex to solve, friends. It is not that easy because they deal with non-linear interactions. A simplified version of such interactions are possible with accepted assumptions, but when we try to solve a highly nonlinear problem in a relatively linear domain, there are some ignorances which will not be able to help us capture the correct behavior of the system. Okay? So, simplified nonlinearity, simplifying the nonlinear interaction of wave Beck to linear models will not help simulate the true results. So, there are some issues. So, one cannot simply take away to the field and install and try with the field tests when you do a simplified analysis. So, this was clearly verified by Fallness in 2002, and Fallness says that let us not attempt to do a simplified linear model analysis for WAKE. Okay. Now, the complexities during this analysis, both experimental and numerical, come from various sources. The first source is the relative subsystem of WAKE. And how are you installing them? How it is position restrained, such as moving system, the appropriate PTO used for this, and the PTO will have linear damping and linear spring. Okay. This will contribute to the complexity of PTO. And then of course, solving complex equations which are leading to nonlinear in nature. Therefore, friends, in general, to start with, all simple analysis assumes the excitation of physical quantities in a simple harmonic form. So, the first step adopted to represent a wave energy converter dynamics is to model this in frequency domain. So, I could say the first step to model a wave energy converter accounting for all these complexities is generally done in frequency domain. So, let us see what are the complexities arise when you start modeling them in frequency domain. Let us take a graphical illustration of this. Let us say look for a wave energy converter system. This superstructure of the system, the superstructure of the system has some substructure. So, we call this as subsystem 1. Okay. So, let us say the wave level is here, subsystem. The subsystem then will have to be supported to the seabed or cushion restraining it. So, once I support it, then I must have a power takeoff system which is embedded here. We call this as power takeoff system, which is subsystem 2. And of course, in this system we have a damper and we also have an equivalent stiffness, which will contribute to the damping and resistance to the power takeoff system. So, looking at this block diagram, let us try to understand the complexities in analogy. So, in simple terms, a WEG design is expressed as a simple spring mass damper system. Okay. So, now if we consider this a spring mass damper system, let us say the WEG system is a floating buoy. I should say a hollow floating buoy, so that the system is positive buoyant. Okay. Now, when the hollow floating buoy is pushed in sea, it will start displacing volume of water around it, which invokes buoyancy. So, this floating buoy, which will have a mass, will also invoke upward force, which pushes this float, and we call this as buoyancy force. So, as per design, we always want to make either buoyancy equal to the mass, in fact the weight, or buoyancy exceed the weight, to make it very simple for installation, right. So, positive buoyant, this is positive buoyant, and this is called neutral buoyant. So, we can design a system like this. I can simply take a spring mass system analogy. I know the shape and size of the body, I can find the buoyancy force, can always find the weight of the body, I can fit them in into any one of this category. Okay. So, once I fit this, I have the geometric design ready. For the geometric design, I can work out the frequency, I could say the fundamental frequency, can also work out the damping ratio for that frequency, right. So, the damping effect should also include damping arising from viscosity and body generated waves. It is not only the structural damping, it is also the medium damping, okay, body generated waves. Which is correct, arising from the medium. So, this arises from the medium. So, I must be able to estimate the damping coming from the medium as well. So, this damping effect is induced externally this damping effect arising from the medium should be included externally, correct? So, structural damping can be internal, but this damping has got to be inserted externally, and we call this as a part of power takeoff mechanism. Okay, and this can be analogous, the buoy analogous to dashpot or the damper and the mass block, which we showed in the previous slide, okay, which we showed in the previous slide, this one. So, the PTO can be analogous to the dashpot and the stiffness, the friction arising from the mass block which is coming to this particular body system. Okay. Now, friends, now the motion of the waves which is one of the important input for the whole analysis is generally described using velocity potentials. Across the ocean, and they are generally helpful in representing first order waves. So, in general we call this as theory based on Airy's. So, we call Airy's wave theory is helpful in doing this primitive analysis, provided the flow is said to be potential. Okay. Then I can use the linearized Bernoulli's equation for small amplitude and large wavelengths and start working out the effect. Okay. So, we will discuss those theories and the derivations useful for the analysis in the next lecture. So, now let us look at the summary what we learned in this lecture. So, friends, this lecture gave us a very interesting idea about the advantages why I should work on the wave energy conversion in Indian coast. We also discussed about the fundamental design parameter I must look at, and then we understood that small scale simple wave energy devices will suit the requirements for Indian scenario. Then we learned what are the output targets, what we want to do from the design. Okay. So, we learned about the Indian scenario and the necessity for wave energy converter. Then what are the target points which we must design? What are the stages which are involved in designing or conceptualizing a wave energy converter? Then how I can arrive at the methodology of developing a new wave energy converter. Then we also discussed about how or what are the factors that govern such design. So, nevertheless, we highlighted the complexities involved in the whole process. So, friends, please stay connected with us to learn more about the design scenarios of wave energy converters. Welcome to this course on marine renewable energy systems, which talks about details in analysis, design and development, hosted by Maritime Engineering Department at IIT Gandhinagar. Thank you very much.